So in I mentioned the SP, D and F subshells when I was going over the Auf Bau Principle to show the shapes of F, SP, D and S. Okay, these, by the way, these occur, as I said, in the first, second, third and fourth shells of the atom. The shells contain subshells. The S subshell stands for sharp. So you have, okay, and you have basically, that's the 1S subshell, okay, and then you have and that's the 2S subshell, okay. So this is the X, Y, and you can also put, I suppose I call that a Y and that Z, okay. X, Y, Z, okay. So it's basically, you got to imagine, these are spheres, okay. And then the 3S, so again that's even bigger. Okay, that's 3S subshell, okay? X, X, Y, Z, okay? So that's the 1S, 2S, 3S subshells. So the S subshell stands for sharp, P stands for principal, D stands for diffuse, F stands for fundamental. That's SPDF, sharp, principal, diffuse, fundamental. See, the names sharp, principal, diffuse, fundamental come from the spectral lines. Right, next the P subshells, okay? So basically, so you got X, R, you got Y and Z, okay? So you got the okay, so that's the px orbital. Then you got that's the okay, that's the py, and then here so you got okay, so that's the pz, okay, so these are dumbbell shapes, okay, px, py, pz orbitals. Total of 6 electrons in the p can occur in the p, and there's 2 electrons per dumbbell, okay. So that's yeah, 2 electrons per dumbbell, 6 instead of 3 orbitals. And then lastly, you've got the D. Okay. These are a bit more complicated. So let's see. So you got X, Y. Okay. So you got okay. So those are between the X and Y axis. So that's called the DXY subshell, okay? And then you got X, Z, and you got okay, so that's PXZ, and then you got YZ, okay, so you got okay, so that's the PYZ, so P, DX, P, XY, so DXY that should be D, not P. That should be D, not P. Okay, dxy, dxz, dyz, okay? Yeah, dxy, dxz, dyz, okay? And then there's two more, which I try to fit in here so it looks a bit better. You got one here, which is, so you got our x, y, okay? And then you got, so this one is the orbit actually lies on the axis. So these, in these kind of cases, the orbitals lie between the x and y axis. In this case, it lies on. Okay. So this is called d x squared minus y squared. Okay. And there's one more, which is where you have the z. Okay. So you have the orbital lying sort of above like that, and then you got a sort of a ring, okay, around like that. It's like a ring shape, okay, going around it, a tube going around it. So this is called the d z squared, okay? So that literally is a ring, like a tube going around it in a ring, and the dumbbell over the z-axis, and this is dumbbells over the x and y, and these are between. So that's the dz squared, dx squared minus y squared, and dx, dyz, dy, dyz, dxz, dxy. Okay, so that's the d orbitals. When I was studying at college 30 years ago, I remember the teacher being completely baffled at how anybody could think of this stuff. I learnt later in my degree how this is all derived. So these orbitals are basically, they come from the orbital, or they come from the Schrodinger wave equation. When you solve it, you get these shapes. So the Schrodinger equation, by the way, there's a maximum 10 electrons possible in the d orbital, and there's 5 orbitals, 1, 2, 3, 4, 5. So each of these can take a total of 2 electrons, okay? So the Schrodinger equation is basically so better if I wrote it out sort of a bit more laid out, but that's the h is Planck's constant. So h is Planck's constant, which is equal to 6.626 times 10 to minus 34 joules per second, okay? So not joules per second, joules seconds. Pi is okay, 2.1415 m equals the mass of electron. Okay. These are partial derivatives with respect to x, y and z because it's three-dimensional. Partial derivatives are a bit like derivatives, but they're to can't really explain it in only 10 seconds. It's you have a function with x, y and z in it. If you have an equation with x, y and z in it, all in it at the same time, a partial derivative is taking derivative of say x only, so y and z are not affected. That's what a partial derivative is. So yeah, you take derivatives say of say x or say y only, but the other two are not affected. Okay, that's what a partial derivative is. That equals the wave function. And then that's the potential energy, and that's the total energy. Okay, so this whole equation describes the electron in a hydrogen atom. Okay, but that's the. I'll just try to write that out a little more so it's a little clearer to. That's the potential energy. Potential energy is the energy any object has when it's sitting still. Okay. Basically, yeah, that's the energy of anything when the thing is sitting still. The kinetic energy, on the other hand, is the energy in motion, and that's the total energy. Okay, so this is Schrodinger, and when you solve this, you get these orbital shapes coming out. Okay. The S, the P, and the V. That's where they come from. Okay, so yeah, Fersht and that. Cheers. Please like, subscribe, comment. That's clear, I think. So these are, I believe, computer simulations of Spdf orbitals. They're using the equations like Schrodinger Equation and other equations to model what they look like on the computer. Okay? Yeah, the dumbbells P and D orbitals to give you an idea of what they look like. So these models, these different images of dumbbells and spherical S orbitals are created using math models. Previously, previously it's been hard to get images of electrons. Okay, it's been basically virtually impossible to get images of what you might call a photograph or an image of an electron because they're basically the velocities are too high. Okay, it's far too rapid an event to be able to capture this. So techniques have been developed which use very extremely short flashes of light. Okay. You need something called atto. Something called is attosecond pulses. Okay. Okay, so nano equals that's nano 10 to the minus 9 of a second, then pico, which is 10 to the minus 12 of a second, and then femto, which is 10 to the minus 15 of a second, and then atto, which you guessed it, is 10 to the minus 18th of a second. Okay? So, yeah, it takes about 150 attoseconds for an electron to move around an atom. Okay, to move around the nucleus. Yeah, this 1 attosecond compared to the length of a second is basically similar to the 1 second compared to the age of the universe. Okay, attoseconds are incredibly short. It's almost unimaginably short. So also the actual pulses of attoseconds, attosecond pulses, they're too weak, okay, they're too weak to get an image on their own. So you have to take multiple. You have to take multiple pictures. Okay. Multiple pictures are required in order to create an image. So yeah. So yeah, this experiment has worked. The creation of I don't have access to the video moment, but the creation of images of electrons moving in orbitals has worked because they're basically using pulses which are 10 to 100 times shorter than previously used. So yeah, as I said, 10 to the minus 18th of a second is a billionth of a billionth. It's a billionth of a second. Okay, so laboratories now are beginning to create videos and images of actual electrons orbiting the nucleus of atoms, but all these previous images I'm showing you in this video are actually created from computer simulations using mathematical models like Schrodinger Equation and other equations. There are a lot of them. Harty-Fock, Wigner integrals, there are names I know, but I've never actually worked with them. So yeah, I'm still having problems with my pneumonia. My lungs are slowly recovering, but it's a long process. If I go a few days active, I'll then find I go a few days when I have to be very, very inactive because my lungs are just hammered. Anyway, that's cheers. There's actually a video of electron moving, but it's slowed down a lot.